Welcome, everyone. Today we are going to demystify Agentic Reinforcement Learning, or RL, and lay out the comprehensive recipe for building long-horizon, tool-using agents. Our target goal here is autonomous multi-turn planning. To achieve this, we will be walking through our methodology, the STAR pipeline, which stands for synthesis, supervised fine-tuning, and reinforcement learning, applied across open-weight models ranging from 1.5 billion to 7 billion parameters. Let's start by looking at the friction inherent in long-horizon planning. When we look at the React inference loop, short-horizon tasks, those with just a couple of think and act steps, enjoy a very high success rate. But long-horizon planning is the true frontier. It is a tangled web of continuous think, act, and observe cycles. Agents face constant constraint collisions, having to balance budgets, strict preferences, and complex logistics all at once. This leads to a state space explosion, which is why even massive proprietary models achieve less than 15% success on these tasks. To put this in perspective, an average long-horizon trajectory takes about 10,300 tokens and 9.2 tool calls. To solve this, we need the right testbed. We use the TravelPlanner sandbox. Our raw materials consist of 6 local APIs, including tools for flights, accommodations, distance, and restaurants. The agent must navigate implicit common sense rules, meaning strictly no hallucinations and logical city-to-city routing, as well as explicit hard constraints, like strict budget limits and specific exclusionary rules like no pets. The major advantage here is that it provides the zero-cost, high-throughput simulation that is absolutely essential for scalable RL. So, how do we build the agent? Enter the machinery, the STAR pipeline. It happens in 3 stages. Stage 1 is data synthesis, where we sample atomic constraints and generate over 10,000 balanced, difficulty-controlled queries via backtranslation. Stage 2 is supervised fine-tuning, or SFT, where we use deep teacher models to execute the React inference, strictly filtering for 100% format and constraint success to create high-quality initial checkpoints. Finally, Stage 3 is reinforcement learning, using GRPO-based optimization with environmental feedback to output our final, long-horizon capable autonomous agent. To build the absolute optimal agent, we have to navigate a vast design space. We've conducted an empirical ablation study to systematically isolate and tune 5 specific dials: reward shaping, model scaling, data composition, algorithm selection, and environmental stability. Let's break these down one by one. Axis 1 addresses the reward shaping dilemma. Our key insight is that reward design is strictly scale dependent, and sparse-only rewards are universally suboptimal for complex tasks. Small models at the 1.5B and 3B scale struggle with credit assignment over long horizons, so they require a curriculum reward, a staged transition from dense feedback to sparse feedback to guide their exploration. Large 7B models, however, possess the intrinsic capacity to directly leverage fine-grained, dense rewards, making those heuristic staged transitions unnecessary and restrictive. But there is a hidden cost to dense rewards, the alignment tax. Overly dense, micromanaged rewards maximize immediate, in-domain task success, but they severely penalize general intelligence. For example, when we applied a dense sum reward to our 7B model, its out-of-domain accuracy dropped from 41.9% to 36.7%. Our golden rule here is to use a semi-sparse macro reward to achieve the optimal balance, preserving general information-seeking abilities. Moving to Axis 2, we see the multiplier effect of scale. Scaling the base model capacity consistently improves success rates, but the actual magnitude of that jump is dictated by the reward design. By moving from a 1.5B to a 7B model size under a sum reward, we saw a massive performance jump from 33.1% to 62.8% success. Ultimately, larger models exhibit accelerated convergence and higher performance asymptotes, proving that base model capacity remains the primary bottleneck. For Axis 3, let's look at data composition, starting with volume. We discovered a 1K data sweet spot. RL requires a modestly sized, high-quality subset of data to activate reasoning. At 1000 prompts, we hit the optimal balance where out-of-domain generalization peaks. Exceeding this pushes the model into an over-optimization zone, causing catastrophic overfitting where out-of-domain generalization plummets to 32.2%. It's not just about data volume, it's also about data difficulty. The ideal training dataset composition is a mixed diet, 40% easy, 30% medium, and 30% hard. Easy queries are crucial for maintaining dense reward signals, while hard queries are essential for teaching advanced constraint satisfaction. If you train exclusively on hard data, you hit a failure state, dropping to 25.9% success because the agent literally starves from a lack of positive reward signals. Axis 4 highlights an interesting inverse law regarding algorithmic complexity. The necessity for sophisticated exploration mechanisms is inversely correlated with base model capability. The 1.5B scale needs help, relying heavily on complex exploration algorithms like ARPO to boost success. But at the 7B scale, the model needs efficiency. Standard GRPO completely dominates here. The takeaway? Stop expending compute on heuristic exploration algorithms if you are scaling the model size. Rely on the raw efficiency of GRPO instead. Finally, Axis 5 is the environmental stress test. We injected random tool unavailable errors during training to simulate real-world API instability. We found that the agent has a resilient threshold and can tolerate occasional anomalies. However, once environmental noise exceeds 5%, we enter a degradation zone. Instability severely hinders successful trajectories, proving that multi-turn tool calling requires highly stable training environments. Synthesizing all these insights gives us our ultimate scale-aware recipe. For universal settings, use the 1K data mix and maintain high environmental stability. Then, match your architecture to the precise RL configuration. 1.5B models should use ARPO and curriculum rewards, 3B models should use GRPO and curriculum rewards, and 7B models should use GRPO paired with macro or dense rewards. And the result of this recipe? State-of-the-art dominance. Our optimally tuned star 7B model comfortably crushes heavily parameterized proprietary models and specialized agents, achieving a 62.8% success rate on TravelPlanner, compared to GPT-5's 15.5% and Kimi K2.5's 11.8%. While we have built the foundation for autonomous long-horizon agents, the frontier still holds open challenges. We must bridge the reality gap from closed sandboxes to unpredictable, open-ended real-world APIs. We also need to map cross-domain generalization to entirely different modalities like coding and GUI interaction. Finally, we must overcome the global backtracking bottleneck, teaching agents to intelligently unwind previous decisions when hitting a dead-end state space. Ultimately, the STAR pipeline proves that algorithmic precision and rigorous experimental design can effectively overcome raw parameter counts. Thank you.